In this video, we're going to introduce simple harmonic motion. So let's get started. So the simple harmonic motion is when the magnitude of the restoring force is proportional to the object's displacement. So a common example is spring force, where we can see that the force that the spring is causing on like a box is proportional to how much the box is moving. Okay, and so we can use this to derive some understanding of velocity and acceleration in a system where we have simple harmonic motion, as shown over here with the springs. So if the force of the spring is the only force and it's proportional, there isn't going to be any other, if there's no other forces like friction causing it to slow down, and we have this simple harmonic motion in this ideal case, we can say that if this spring force is going to be the net force of the system. And so when we have that, we can say that the mass times the acceleration is equal to negative kx, or change in x. So this would be the acceleration in the x direction, or whatever direction this change is in. And so we can see that when the box, and so we can use this actually to derive some things, and we'll see how we use that when we start talking about these scenarios. So let's say this box is pulled to an endpoint and it's allowed to oscillate back and forth. So let's compare the velocity and acceleration and the force at each position. So the velocity, when it's all the way scrunched up, well, if it's all the way at this point before it comes over this way and then it starts heading back this way, this velocity is going to be at a 0 because it stops for one brief second before going back the other direction. And so now, what is the acceleration going to be? Well, we can see that the acceleration is proportional to the change in x. So when the change in x is the greatest, the acceleration is going to be the greatest. And since this change in x is the greatest when it's scrunched up, and we'll say this is x equals 0, and this is like the equilibrium position, then the acceleration is going to be a max acceleration. And so for the same reasoning, with the force being proportional, the force will also be a max. Okay? And so now let's look at equilibrium. At equilibrium, now the change in x equals 0. So if the change in x equals 0, then the force and the acceleration will all equal to 0 because there's no change in x, but this block is still moving, right? It was scrunched and now it starts moving this way. So the velocity is actually going to be at a maximum right in the center. And so now, for the same reasons as a scrunched up spring, when it's spread out or pulled out as far as it can be, the velocity will hit 0 on this side, and the force will be at a max, and the acceleration will be at a max. But in this case, the force is in this direction, and the acceleration is in this direction, but in this case the force is in the opposite direction. But their magnitudes will be at a maximum at the end points of oscillation. Okay, and so there's other type of simple harmonic motion. One other common example is if we had a pendulum, where we have like here, and there's like the equilibrium position, and it oscillates back and forth. And so this would also be a type of simple harmonic motion, but we'll learn more about this in later videos, but it only works for small angle approximations to be a true simple harmonic oscillator. But we'll talk more about that in later videos. For now, let's do an example with the springs. Okay, so we have a 5 kilogram mass is attached to a spring with this spring constant on a frictionless table, is pulled 0.2 meters from equilibrium, then released. Okay, so when is the acceleration at a maximum and a minimum, and what is the magnitudes? Okay, so let's draw out this scenario first. So we have a spring, okay, and it's attached to a box of mass, we'll just say m for now. And so let's say this is the equilibrium position. And so this box is pulled a distance out to here, and this is 0.2 meters. Okay? And so we need to find when it's at a max and a minimum. So let's write what variables we have. We know the mass of the box is 5 kilograms. We know the spring constant is 10 newtons per meter, and we know it's pulled 0.2 meters, so that's going to be the change in x. Okay, so let's figure out what that's going to be. So we know, first off, find the acceleration at a minimum is definitely the easiest part, because the acceleration at the equilibrium position, the acceleration right here, is just going to be equal to 0. So this, at this point right here, the acceleration is at a minimum. And so we can say, like, a minimum is equal to 0. But the maximum is a little more tricky, because we know where's the maximum going to be. Well, it's going to be a max at 2 spots, because once it's released from rest here, the box is going to travel this way, it's going to reach its max point here, and then travel back this way, and continue doing that. So there's 2 points. We have a max at when it's, let's say when it gets like to its point over here, this will be a max, and then when it's all the way out at stretched position, it'll also be acceleration max. So to calculate this, we can use our equation that we derived previously, where we had the force of the spring equals negative k delta x. But since we're on a frictionless table, this is the only force. If we draw a free body diagram real quick, yes, we'll have gravity and normal force as always. Well, not always, but in most cases. But when it's being pulled out, we just have the force of the spring. There's no other force, so this will be the net force. So this is just going to be mass times acceleration. And the acceleration we want is the max acceleration. So that's going to be when the change in x is at its max point, which we already defined it as its max point over here. Okay? And so we can, since we're just worrying about magnitudes, we don't need to worry about this negative, because this is just saying the force is in the opposite direction as the negative change, or as in the change of x. Since we're just looking for the magnitude acceleration, we can drop that out, and we can solve for acceleration by saying k change in x over m. And so we have all these variables now, so we can just plug these in, and we get 0.4 meters per second squared is equal to a max. Alright, so that's all I got for this video. In the next video, we'll start talking about more about the 2 main oscillators that we're looking at, springs and pendulums, and how we can derive frequency and periods of those oscillations. So make sure you stick around for that, leave your questions down below, and thanks for watching.